What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. And today I have a challenge for you. We've discussed single body objects, single body torque problems, where we're looking at objects that are in an equilibrium and solving net torque expressions based on what we see. Today's challenge is called the Going Mobile Lab, and it's a silly play on words, right? It's not great. Oh, by the way, I got Mira Evans and Catherine Sobel over here thinking it's Tuesday. It's Thursday. Don't give us extra days in the week. Come on now. We don't need that. It's almost the weekend. It's not Tuesday. It's Thursday. Back to the challenge. The challenge is I'm going to give you two torque sticks. Torque sticks are my hook sticks. And I'm going to ask you to try and experimentally, only using a set of masses and a set of monkey bars, to go ahead and determine the mass of each stick. So the challenge is kind of this, right? The setup is essentially this, right? I'm going to give you two hook sticks. Over here, you've got a set of monkey bars. On the monkey bars, the only caveat that I have, and there's good reason for it, the only caveat that I have is the first stick must be hung off center. So I've got 1, 2, 3, 4, 5, 6, and then 5 more. We've got 11 hooks on bottom, 2 on top. We're going to hang the top one off center like this. Make sure that it's off center. We're not going to hang it on the middle hook. We want it to be unbalanced. I'm going to try and find the mass of this stick. I'm actually trying to find the force of gravity on this stick. That's what I'm looking for. So I want to make sure that I don't have my pivot point, the spot it's hung at, directly above that force of gravity, the center of mass. If I did, then that force of gravity is not going to cause a torque. It's going to be tough to figure out that force. Not impossible, but it's going to be tough. I'll have to end up using a torque equation and then go into an F net, and I don't want to do that. So the first caveat is hang both sticks off center, and the setup looks like this. I've hung one, and obviously it's not balanced. It's off center. The force of gravity is causing it to rotate in that direction. The other thing I have to do is take the other hook stick, again, off center, and hang it from the furthest hook away. So I get something like this, where these are both together, and it starts looking like a child's mobile that hangs above their crib, like my daughter has. So we'll go ahead and hook this up, bang, get it on there, and bang, off center, and this is our starting point. Now, the challenge is to continue to add masses to both of these sticks until we get both of these things level. So obviously you're playing with torque and you're playing with location of mass, trying to get these things to balance into a rotational equilibrium. I've already done that over here. So let's go ahead and take a look over here. And the weird thing about it is when you add masses to one side, it actually jacks things up a little bit. So I come over here and I already have this thing totally balanced. Okay, I've got this stick balanced here. I've got this stick balanced here. The weird thing about this actually is that as I add masses to the second stick, it throws this balance off. So when I'm thinking about doing this, I want to go ahead and add masses to this side first, and then add masses to this side next. So clearly, this stick is applying a force through this point. When I think about this whole stick as a system, on the big board or the top board, it's all applying a force right here. Now this board has torque also. There's the center of mass of this board, again, off center here, 10 centimeters away from the hook it's hung from. Then I've got this mass here in order to balance this. Then I come to the top stick and I have this as well. So this is my setup. Let's go ahead and take some data on what we did. Sorry, Mira and Catherine, I'm going to have to erase your wonderful, confusing notes. So we're going to erase those right now. Let's look first at the bottom stick, okay? So we'll call this the bottom stick. We're going to separate both of these into two different problems. But here's the bottom stick. Here's my hook or my pivot. And then every hook we have on this hook stick is 10 centimeters apart. So that helps us figure out location of masses pretty easily. I don't need to get a meter stick out or anything. They're all 10 centimeters apart, and we can make that assumption. They're pretty close to 10 centimeters apart. Okay? So let's think about this. If this is where this is one hook away from the center of mass of this board. This is FG for the board. And then on this same stick, on the same side of the center of mass, I have a 100-gram, 10 centimeters away, one hook away I have a 100-gram mass over here. So 10 centimeters away from this, which would be, there's a hook here and a hook here. 20 centimeters away from my pivot. And then on the opposite side, let's count. 1, 2, 3 hooks away. 1, 2, 3 hooks away. There's a 200-gram mass hanging. We're going to put these around here on the hooks. Again, every hook is 10 centimeters. This is how it balances. This is the system that is balanced over here. Okay? This is the bottom stick. Now this total mass is this board plus the added masses, so consider that when I think about the top stick. The top stick is also off balance, so I've got my off balance hook and my middle hook, and then there's a hook here, and then there's 1, 2, 3, 4, 5 hooks, and there's 1, 2, 3, 4, 5 hooks. This is what the stick looks like. Let's figure out. On the off-center side, right, where there's 1, 2, I'm hung here. I'm hung right from here. Axis of rotation is there. On the short side, 1, 2, 3, 4. On the short side, I've got 3 masses, and on the much longer side, 1, 2, 3, 4, 5, 6 is where I have the stick. So I'm going to go ahead right here and say this mass is the stick. We'll just show it like a circle, but the entire stick is right here. That's where the stick is located. Think about what the mass of the stick is over there, okay? On the same side as the stick, right here, I have obviously there's the center of mass, so FG from the board, that's there. I also have on the long side of the stick a 200-gram mass. That's sitting there as well. That's right at this hook. Okay, so 10 centimeters away. At that hook, there's a 200-gram mass. And then going down the line, away from the axis of rotation, on the first, second, and last, I go 50 grams, 500 grams. Right here is a 50-gram mass. Over here is a 500-gram mass, and over here is a 1 kilogram mass. So this is the first stick, this hook, second hook, and fourth hook. All right? We can get closer. This might be tough to see. Let's get closer. Woo! Top stick looks like this. Pause it if you need to, but this is how that hook or this thing is set up. And again, as it's set up this way, I may have bumped it a little bit. As it is set up this way, both are balanced, which means the net torque here is 0, the net torque here is 0, and on the top stick, we have this whole stick being supported as well. This bottom stick is a part of this top stick. That's why you see so much mass over here. Your job at this point, if I think about my job, it is to go ahead and solve for the FG and eventually the mass of both of these sticks. Okay, this is your challenge. I would probably start with a net torque expression, and then it's on the bottom stick, and I would solve that for force of gravity on there. I'd solve for mass there, and then I would go ahead and approach the top stick. So bottom stick first, top stick second. We can go ahead before we leave here and write a net torque expression for the bottom stick. We can go ahead and try to figure this one out. Let's try it ourselves. Again, like always, if you want to do this yourself at home, pause it, do it. Otherwise, I'm going to kind of walk through it a little bit here in class for the bottom stick. Let's think. It's balanced. It's not rotating, so the net torque is 0 Newton meters. Let's think about what I got here. I've got all these forces going this direction, causing torques there. All these forces causing torques in this direction. I would see the torque from FG board. That's my go-to. That's what I'm solving for. Plus the torque from the 100-gram mass minus the torque from the 200-gram mass. If I keep breaking this down into my variables, FG board is going to be force of the board, or mg, times the distance to the board, which we'll call it r board, That's the distance between the pivot and here, and that's 10 centimeters per hook. There's 1 plus the torque of the 100 gram mass. Well, 100 grams would be 0.100 times 9.8 meters per second squared. That's G times R for the mass, for the 100. And that's 2 hooks from the axis of rotation. Minus the torque for the 200 gram mass. 200 gram mass, 0.200 times 9.8 meters per second squared times R for the 200 gram mass. And that is going to be how many hooks away? 1, 2, 3 hooks away, so 30 centimeters. All right? So we can go ahead and solve this. And what I end up with is known as my mass experimentally. You're going to take your experimental mass and compare it to a theoretical mass. And I'll get the theoretical mass for you here in a second. You go ahead and work this problem out. I will go ahead and get us a theoretical mass for this system. I get around 429 grams is theoretical. This is when I put it on the balance, this is what it is. This is how much it actually is, right? This is my actual value. My experimental value is what I get when I do the actual math from the data I collected, okay? This answer right here better end up right there, and we do the entire process all over again. If you got questions, drop it in the comments. Send me an email or ask me in class. But until next time, see ya!